Okay, we're back with the last video for topic 8.11 AP Cal curriculum. We're doing volume washer method revolving around the X or Y axis. In this video, we're going to do examples revolving around the Y axis. So here we are. We're going to let R be the region bound by the curves f of x equals 3x plus 1 and g of x equals 4 to the x in the first quadrant. We're going to find the volume of the solid generated by revolving R around the Y axis. As always, we're going to start by graphing the region. We have the line f of x equals 4, or sorry, g of x equals 4 to the x, and the line f of x equals 3x plus 1. Those are going to intersect. Well, let's do this a little different. Make sure that I get a region big enough that I can draw a rectangle in. All right, they're going to intersect at y equals 1 when x is 0. They're going to intersect when x equals 1 at y equals 4. And this time, we're going to revolve about the y-axis. So our rectangles are going to be perpendicular to the y-axis. And when we revolve, we're going to see a washer that looks like this. Now, you know me by now, if you've watched the first two videos, I prefer to do it with one large rectangle, and then we'll generate the volume of that cross section. And then we'll subtract out the volume of a smaller cross section. So this time we'll have dy. Now we need to know what the radius is here. So to do this, like we have always done before when we're doing cross sections and other things, we're going to invert the axes. It means we're going to solve each of these for x instead of y. So here I have y equals 3x plus 1. Here I have y equals 4 to the x. If I solve this linear equation for x, I get y minus 1 over 3 is equal to x. So here we have y minus 1. Oops, nope, sorry. Let's finish this before we do that. And over here, if I take the ln of both sides, I have ln y equals ln 4 to the x. I can bring the x outside and get x equals ln 4. And then that becomes ln y over ln 4 when I divide by ln 4. So x equals ln y over ln 4. Or you could have written it in logarithmic form. So that's just x equals log base 4 of y. But in this case, now we've solved it for x. We're going to re-graph these with the y-axis on the horizontal axis, the x-axis on the vertical axis. Okay, now still y, we're going to be concerned with y equals 1 and y equals 4. And this red curve is now going to be here. We're still going to be concerned with x equals 0 and x equals 1. I should have waited till we do that. See where this intersects when we do it. All right, we still have a line now that's going to be x equals y minus 1 over 3. Y minus 1 over 3. So x is going to be 0 when y equals 1. So this is going to cross here. And then our rectangles, our large rectangle, let's do that in red since we started out in red. For our top function, this is going to be the curve, the logarithmic curve, x equals ln y over 4. ln 4. So the radius of this first disk is going to be ln y over ln 4. And so the volume of one of these disks is going to be pi times the radius squared, which is ln y over ln 4 squared times dy. And of course, This was when y equals 4. So for all of those volumes of that large outside disk, we're going to get the integral from y equals 1 to 4. Bring the pi out front. The inside is going to be ln y over ln 4 squared times dy. And that's the volume of the large outside disk. The next thing we're going to do is we're going to subtract out the smaller inside disk. I'm going to draw that separate. So the smaller inside disk that we're going to subtract out. We're going to need the radius for it. Its width is going to be dy like before. So this time we're looking at, let's just go ahead and draw this blue rectangle whose height is the linear curve. And this blue rectangle is going to be x equals y minus 1 over 3. And so the radius of this disk is going to be y minus 1 over 3. So the volume of one disk is going to be pi times the radius, y minus 1 over 3 squared times dy. And the volume of all of those disks integrated from y equals 1 to 4, going to bring the pi outside as a constant multiple. That's y minus 1 over 3 squared times dy. And now to get the volume of the region, we subtract large outside disk minus small inside disk. So we end up with pi times the integral from 1 to 4 of ln y over ln 4 squared dy minus pi times the integral from 1 to 4 of y minus 1 over 3 squared dy. Or if you like using the formula, you can say that's the pi times the integral from 1 to 4 of the outside curve, the upper curve, which is ln y over ln 4 squared. Sorry, it's ln 4 squared. Minus the lower curve, y minus 1 over 3 squared times dy. Most of the time, if you have to do it on non-calculator part, you would just set up the integral and solve, or you don't want to solve it. Here, I'm going to go ahead and solve it on the calculator and get math 9. I'm going to do the integral difference first, and then I'm going to multiply the answer by pi. So I'm going to have the integral from 1 to 4. And inside here, I'm going to have ln 4, close parentheses on the ln 4 divided by, ln. I'll put x's in the calculator because it's the TI-84. ln 4 in the denominator, close parentheses on that, close parentheses again, square it, and then that multiplied times the variable integration. I'm using x's in the calculator. Now, that's my first integral minus my second integral, which is going to be math 9, 1 to 4. And that's going to be the y minus 1. I'm going to put in parentheses. I'm going to put the whole thing in parentheses right now. So, fraction. I'm going to put y minus 1, or sorry, x minus 1 in the calculator, over 3. Then parentheses. I'm going to square that. Then integrating that again in the calculator with respect to x. Now I'm going to get the integral difference, and I'm going to multiply that by pi. And I get 1.103 or 1.104. I'm always going to chop instead of round, but if you round correctly, units cubed. And that's the first example. Let's do another example with those. This time, let's let the region R be bound by the curves f of x equals x to the fourth and g of x equals 8 times x in the first quadrant. Find the volume of the solid generated by revolving R around the y-axis. Once again, let's graph. F of x equals x to the fourth is parabola-like. And the line y equals 8x is a line to the origin. These two are going to intersect at x equals 0 at the origin. And when x equals 2 and y equals 16. Since we're revolving about the y-axis, we're going to be looking at rectangles perpendicular to the y-axis. So I'm going to solve these for x. I'm going to get y equals x to the fourth. So that y to the 1/4, or the fourth root of y, equals x. And here y equals 8x. So x equals y divided by 8. I'm going to regraph this with the y-axis on the horizontal axis. And this time when I flip it over the line y equals x, the y to the x equals y to the 1/4. And then the curve x equals y over 8. And this is going to intersect when y is 16 and when y is 0. So now I'm going to do the top disk, that big disk, with dy. The radius this time is going to be the upper curve, y to the 1/4. So this is going to be, y to the 1/4. So my integral for the volume of this one disk is pi times the integral. I'm not doing the integral yet, I'm doing one disk. It's pi times the radius squared. Y to the 1/4 squared is y to the 1/2, y to the 2/4, so y to the 1/2. So that would be equal to pi times the square root of y, or y to the 1/2, times dy. To get all of that integrated, if we revolve the top curve around and get the solid, we would have the integral from y equals 0 to 16, pi on the outside because it's constant multiple, and this would be the square root of y times dy. Then we're going to subtract out the lower curve, the lower part of the solid, which is going to be that inside disk. I'm going to draw that disk by itself here so it doesn't get too cluttered. I need a radius. My height is still dy. The radius this time is y over 8. So the volume of one of those is pi times y over 8 squared. That's an 8. Times dy. And all of them together are going to be 0 to y equals 16 again. And this is going to be pi on the outside because it's constant multiple, and y squared over 64, or just y squared over 64 times dy. And if I want the volume of the entire solid, I'm going to do the integral of the large outside solid minus the inside solid. So I'm going to do from 0 to 16 of the square root of y dy minus pi times the integral from 0 to 16 of y squared over 64. You could bring that 61 over 64 out also. If I like the formula better, I'll just do pi times the integral from 0 to 16 of my top function, which is the square root of y squared. Oops, did we square it? Oh yeah, we squared it when we got to square root of y. All right, so this is going to be square root of y. That's the y, the 1/4 squared, right? Minus y squared over 64, because we've already squared that, times dy. And both of those will give you the same volume. If we type that in the calculator, I'm going to go to math, 9, and I'm going to do 0 to 16. I'm going to go ahead and do the square root of y, square root of x, sorry, because I'm putting in the calculator. It's going to be x, and I'll multiply by pi when I finish with this, minus the integral math, 9, 0 to 16. And this one's going to be y squared over 64, or x squared in the calculator, with respect to x. And when I finish, I've got to multiply it by pi. And I get 67.020 or 67.021, depending on if I round or chop. 67.020. I'm always going to chop just because I won't round wrong that way. That's units cubed is my volume. And that's how we do washer method revolving around the y-axis.